Bismillahirrahmanirrahim. I welcome you to the 11th lecture of the series of lectures on advanced computer architecture. Today, after a brief review of what we discussed last time, I will discuss in details three different types of hazards which can exist in case of pipeline data path. Last time we talked about the design of pipeline data path. Here we started with the definition of the pipeline data path, and we discussed the performance of data path which is designed using either multi-cycle or pipeline concepts. Here in this comparison, we found that the performance of pipeline data path is 2 to 4 times better as compared to the multi-cycle data path. We also discussed the key components of the pipeline data path. We gave special importance to the use of pipeline registers, and we discussed in details what is the role of these registers in performing operations in parallel by using effectively the different parts of the data path. However, at the end, we noticed that due to the use of more than one sections of the data path simultaneously, we may get some problems at certain occasions. These occasions are known as the hazards which may exist while executing instructions in pipeline data path. Today, I will discuss one by one the three different types of hazards which may exist in pipeline data path. First of all, I will be talking about the structural hazard. The structural hazard occurs when we attempt to use the same resource in more than one ways at the same time. For example, a single memory port may be accessed for instruction fetch as well as for data read at the same clock cycle. So this type of hazard can create problem, as you can see from here with the help of this diagram, that if the first instruction is the load instruction, then in the first clock cycle the memory is accessed to fetch the instruction, whereas in the fourth clock cycle the same memory is accessed to fetch the data or to read the data from the memory. However, as you can see from this diagram, in the fourth instruction, in this case, is also in the instruction fetch mode in the fourth clock cycle when the first instruction is fetching data from the memory. So this in fact leads to a hazardous situation when one attempt is made to read an instruction from the memory, and from the same memory an attempt is made to read the data. So this type of situation is a problemsome situation. Therefore, we have to take care of this. Similarly, another situation of the structural hazard may be when two different sources try to write to single write port in the register file. In order to explain this situation, let us consider the use of pipeline data path as a 5-stage pipeline as well as a 4-stage pipeline for different types of instructions. As you know that the load instruction can be executed by 5 stages. That is, the first stage is the instruction fetch stage. Second is instruction decode and register read. Third is the address calculation. Fourth is the memory read. And fifth is the writing the value read from the memory into the register. Whereas the register type instruction, where, for example, the register type instruction add can be fetched in the first clock cycle, it is decoded and registers are read at the second stage. The third stage is one when this instruction is executed, required operation is performed onto the data, and at the fourth stage, the data is written into the memory. Now, if our control unit allows to use the pipeline data path as a 5-stage as well as a 4-stage unit, then the structural hazard problem may occur, which is quite obvious from this diagram. Here you can see that the load instruction, which is fetched in the third clock cycle, it is in the write back state in the 7th clock cycle. Whereas the following R-type instruction, which is fetched in the 4th clock cycle, is also in the write back state in the 7th clock cycle. So this means that in the 7th clock cycle, the load instruction as well as the R-type instruction, they are trying to access the write port. Whereas we know that in the register file, there is only one write port. So this means there is a structural hazard. There are two possible solutions in order to avoid this type of structural hazard. You can see from this diagram over here, one way is that we introduce a bubble at the 6th clock cycle, which will delay the write operation by the R-type instruction. Bubble, as I am using this terminology for the first time, is in fact a stall operation, which means that we stop the operation for one clock cycle and we wait till the end of the clock cycle and start of the tick for the next clock cycle. And then the required write operation starts. The alternative is to delay the write operation for the R-type instruction by one clock cycle. It is shown here in this slide, where instead of introducing a bubble, we are just delaying the write operation for the R-type instructions. So these two solutions are the possible ways to eliminate the structural hazard for write operation. The structural hazard, therefore, can be reduced or eliminated by either including a stall operation or by providing additional functional units. As we discussed earlier, the stall operation always degrades the performance of the system. For this purpose, let us consider this example where we suppose that the data reference instructions constitute 40% and processor with structural hazard has a clock rate of 1.05 times higher than the processor without hazard. We know that the average instruction time is given by the product of clock cycles per instruction and the clock cycle time in the ideal situation. As in this example, the clock cycles per instruction can be calculated as 1 plus 0.4:1. 0.4 corresponds to the 40% memory reference instructions multiplied by the clock cycle time and divided by the clock rate of the processor in case of structural hazard. This gives us a value which results in 1.3 multiplied by the clock cycle time of ideal. It shows that the processor without structural hazard is 1.3 times faster as compared to the processor with structural hazard. So this shows that in fact increasing the clock rate to remove the structural hazard in fact degrades the performance. Similarly, if we include stall, that also degrades the performance. The effect of the stall on the overall performance we have already talked about, and you can refer back to number of examples given at the end of your book in order to further understand this concept by solving the numerical examples or numerical exercises given in your book. The second approach for removing the structural hazard is the addition of more than one functional units. For example, we can eliminate this memory structural hazard by including two memory units, one for the instructions and the other for the data, accordingly known as the instruction memory and data memory. No doubt this approach is normally used in almost all today's processors, but in reality it is quite expensive solution, because we know that including two memory units means that we also have to include two caches. The concept of the cache we will discuss at some later stage. I think now concept of structural hazard and different techniques which are used to minimize or remove these hazards will be clear to you. So now I will start with the discussion on the data hazard. The data hazard is one where one attempts to use an item which is not yet ready. For example, in case of the washing machine pipeline, if one of the sock is in the dryer and the other sock is in the washer, when the dryer finishes its operation and passes on the information to the folder, which means passes on this sock to the folder cannot fold it until and unless the second sock is available. Similarly, with reference to the processor's pipeline structure, we can consider different examples, and I will explain to you what are different situations which can occur. We know that pipelining changes the relative timing of instruction by overlapping their execution. Data hazard occurs when order of the operand read-write is changed vis-a-vis sequential access to the operand, which gives rise to the data dependency. We can discuss this data dependency with the help of this example program. Here in this sample program, as you can see, the first instruction in this example is add R1, R2, R3, which means that we want to add the contents of register R2 and R3 and place the result in R1. Whereas the next instruction, that is the subtract, and all the following instructions, they are using the contents of R1 as one of the operands. Now let us see the execution of these instructions in a pipelined data path. As you can see from this graphical representation, the first add instruction will write the result of the execution in the 5th clock cycle in the write register, which is shown here as the write back stage. Whereas the second, third, and fourth instructions, that is subtract and OR instructions, need this data in 3rd, 4th, and 5th clock cycles. This shows the data dependency of the 2nd, 3rd, and 4th instruction onto the results of the first instruction. So this means that the 2nd, 3rd, and 4th instruction will not get the correct data till the end of the 3rd, 4th, and 5th clock cycle. Hence, we have to look into this situation and see how we can avoid this situation. For this purpose, let us look into this next slide, where you can see that we can avoid this problem by introducing 3 stalls, that is, by introducing 3 bubbles over here in the 3rd clock cycle, in the 4th clock cycle, and in the 5th clock cycle. Then the subtract instruction will get the correct data from the register R1 on the completion of the execution of first add instruction. However, you can see that the introduction of these 3 stall operations very badly affect the performance of the pipeline structure. There are other ways also to resolve this issue. One of the most commonly technique used is called the forwarding. Forwarding, in fact, uses the data available in certain internal pipeline registers at different stages of the pipeline data path. For this purpose, let us have a look onto this diagram and see how we can find out the data from pipeline registers at different stages in order to overcome this problem and reduce the number of stalls to eliminate the data hazard. Now you can see over here that the pipeline register between the execute and memory stage contains the result of the execution of the first add instruction at the end of the 3rd clock cycle. Now, if we look into the second instruction, that is the subtract, this subtract instruction needs this data at the beginning of the fourth clock cycle. Therefore, what we can do is we can obtain the data directly from the pipeline register and make it available to the execution unit over here instead of reading the data from the register section. So this way we can pass on the data to the execution unit before it is stored in the actual destination register. This process is known as the forwarding process. Similarly, if you look into the data requirement for the add instruction, the add instruction needs this operand, which is the value of register R1. It is available in the pipeline register between the memory and the write back stage. Therefore, we can pass on this information at this stage directly to the ALU instead of providing the operands from the registers, register A in this particular case. Whereas, if we look into the status of the write back register during the clock cycle 5, the result is written into the write back register during the first half of the clock cycle. Therefore, it can be read in the second half of the clock cycle by the register stage of the OR instruction. So this shows that we can eliminate data hazard in certain situations when the data is available in one of the internal pipeline registers before it is needed by some functional stage. As we discussed over here, for the subtract instruction, the required operand is available in the pipeline register of the execution and memory unit. Therefore, it will be passed on directly from the pipeline register to the ALU at this stage, and similarly for the following instructions. However, there may exist certain situations when the forwarding is not possible. For this case, let us consider this example over here, where the first instruction is the load instruction and the second instruction is the subtract instruction. We know that the load instruction will obtain the required operand only after performing the read from the memory. So this shows that the required value which is to be stored in register R1 by the load instruction, it is not available till the end of the fourth clock cycle. Whereas in this small 2 instruction program, the subtract instruction needs this operand at the beginning of the third clock cycle. So this means that the forwarding fails in this situation. In order to deal with such a problem, we have to insert a bubble, and which means that the overall performance will reduce depending upon what is the actual situation. Now, at this stage, I would like to explain to you how we can design the hardware for the bypass circuit. For this purpose, let us have a look onto this diagram once again, where you can see that the pipeline register for the execution and memory stage, it contains the values of RS, RT, and RD for the first instruction. Whereas the pipeline register at the execution and memory stage for the second instruction contains the value of RS, RT, and RD of the second instruction. Now over here, if we compare the contents of RS of the second instruction pipeline register with the value of RD from the first instruction pipeline register, then we can find out the condition when it will suggest us that it may be a data hazard, and we can perform a forward operation with the help of this thing. Second situation may arise with respect to the third instruction when the contents of the pipeline register of the memory and write back stage are to be compared with the contents of the pipeline register of the execute and memory stage. And again, the source register is to be compared with the destination register. If these two are equal, then this shows that it is a suitable condition for forwarding. Now, as an assignment, please you design a circuit for the implementation of forwarding path in order to avoid the data hazard which may be taken care of by the forward circuit. So, with this much discussion about the data hazard, let us move on to the control hazard. Control hazard occur when we attempt to make a decision before the condition is being evaluated. For example, for a branch instruction, the next instruction address is determined after the instruction decode and register read, because the condition is evaluated in the execution stage by subtracting the two registers and determining whether the jump condition or the branch condition is satisfied or not. But we, in a pipeline data path, have to fetch the next instruction in the second clock cycle. So this means that the instruction being fetched during the second or the third cycle from the present jump position may or may not be a valid jump instruction. These situations are described as the branch taken and branch not taken. Branch taken means that the PC plus 4 has changed its value to a new target value, whereas the branch not taken means that the PC plus 4 is not changed. These type of situations can be taken care of by using different techniques, which I will describe over here with the help of these examples. So let us have a look onto this sample program over here, where you can see that this small program has got the first instruction as a simple add instruction. Second instruction is a conditional branch instruction, and the third instruction is a standard normal load instruction. Here, branch if equal. We have to look into this particular situation. Here, the condition is evaluated at the third stage, whereas the next two instructions will be fetched if they are available in the overall program. So this means that now in this particular case, if branch is to be taken, then the next instruction load is a wrong instruction which would have been fetched into the pipeline data path. So this means that in order to avoid this situation, we have to stall for 3 clock cycles, because we know that the result of the condition will not be available till the end of the 3rd clock cycle from the fetch of the branch instruction. However, the number of stall operations can be reduced to 2 by including some special hardware to the ALU, which may evaluate the condition in the beginning of the clock cycle instead of at the end of the clock cycle. This hardware, however, is a very simple circuit. It may be exclusive OR gate to compare the contents of 2 registers. So this way we can reduce the number of stalls from 3 to 2. There are a number of other techniques which can be used to reduce or to eliminate the number of stall operations in order to overcome the branch hazard or the control hazard. These techniques are known as the delay branching, the branch prediction. Further additional techniques are known as the multiple stream, prefetch branch test, and loop buffer. I will talk about these techniques one by one. So let us first of all consider the delayed branch. From the delayed branch, we actually mean that we can delay the actual branch operation by introducing some other miscellaneous instructions after the conditional branch instruction. As you can see from this diagram over here, that after the branch equal, a miscellaneous word is used. This miscellaneous instruction may be some arithmetic or logical operation which is not using the result of this branch operation at any stage. And if we do not have any such instruction in the program, we can write a no operation at this stage. And if there are 2 stalls are required, then 2 no operations will be used before writing the next instruction. So this means that in this particular case, when 2 no operations are included, they will automatically delay the execution of the program by 2 clock cycles. However, this method is not a very efficient solution for overcoming the control hazards. So this shows that the control hazards are one where we cannot completely eliminate the stall operations. Hence, there will be some degradation in the case of control hazards. However, we can minimize this to either 1 stall operation or keep it up to the 2 stall operations. Let us discuss this with the help of another technique, which is known as the prediction technique. The prediction technique is one where we make a guess. We make a guess in the beginning, and we can design our circuit based on the concept that the branch is always taken or the branch is not taken. So this type of guess, in fact, reduces the overall number of stalls required to eliminate these hazards. For example, if we have to execute a loop which is to be repeated, say for 1000 times, and if the last instruction of the loop is, say, branch if not equal, and we have designed this based on the concept that are based on the prediction that branch is taken. This means that this prediction will be successful for 999 times and it will not be true for one time. So this means that we can have only one stall operation for 999 times and only two stall operations once for the evaluation of this loop. So this shows that the prediction technique therefore minimizes the number of stall operations required for handling the branch operation. The next, we have to talk about the multiple stream technique. Here we use two pipelines instead of one, and we prefetch a branch into one pipe, evaluate it over there, whereas the second pipe continues performing the other operations, and when the condition has been evaluated, the first pipe passes on this information and it evaluates or it performs the required operation. However, this type of technique has its own limitations. The basic limit is that it leads to the bus and register contention, and multiple branches lead to further pipes being needed. The other technique is known as the prefetch branch target technique. Here the target of the branch is prefetched in addition to instructions following the branch. This technique keeps target until branch is executed. The other next method is known as the loop buffer technique. The loop buffer technique is relatively a faster technique, and it uses very fast memory. It is maintained by fetch stage of the pipeline. It checks buffer before fetching from the memory. You can see it from this figure over here that the branch address is made available on the line, whereas the loop buffer is used to hold the information about the loop conditions. Now at this stage, we have discussed almost all techniques to resolve the control hazards. This completes our discussion on hazards today. So if we look into this discussion, what we have talked about today is that what are the structural hazards, how these structural hazards create problems, and how these problems can be resolved. Now I would like to tell you that you please go through some problems given at the end of Appendix A in your book and solve these problems regarding the structural hazards. Then we discussed in details the data hazards. While talking about data hazards, we considered different situations, and we found that except one particular situation, that is the first instruction being the load instruction, and the next instruction is a register type instruction which needs data from the previous register of the load instruction, we can resolve this problem by using forwarding. However, at this stage, you please note that this particular discussion has been focused onto the integer type of data, whereas floating point data has got its own problem and it has to be dealt with in a different way, because floating point data is executed in more than one cycle. I will start discussion onto the floating points and hazards in floating point data from next time in details. Then we discussed the control hazards. The control hazards basically are very typical hazards where we cannot avoid completely the stall operation. If we are using prediction technique, then we can reduce the stall minimum to 1 when this prediction or the branch is taken. Whereas if our prediction is wrong, then in that case it requires 2 clock cycles or 2 stall operations. So this particular situation explains all the types of hazards which we can deal with. Now what I suggest you is that you go through your textbook and particularly consult the Appendix A and study this chapter in more details. Also solve some examples given at the end of the chapter. Now we have finished with our basic review of the concept of pipeline architecture, the multi-cycle architecture, the single cycle architecture for the data path design. We have also been talking about the design of the control units for these 3 types of data paths. I hope that with this much introduction about the design of data path and its control unit, you will be feeling comfortable to understand our next topics, which we are going to start from the next lecture. In the next lecture, we will be starting with the instruction level parallelism, where the instruction level parallelism actually means that how instructions are being executed in parallel. However, please note that in today's discussion, we have focused the integer type of data, whereas from the next lecture, we will be considering the floating point data. The floating point data has got its own problem, particularly with reference to the data hazards and control hazards. Because the floating points usually require more than 1 execution cycles. Therefore, different types of situations may arise when some more complex instructions may require longer time for execution purposes. For example, multiply instruction usually take 20 to 25 instruction cycles. The divide instructions may take 30 to 35 instruction cycles. So considering this, we will be talking about different techniques how to resolve these type of problems. Now with this much introduction to the data path design and the control design for integer type data, I hope that you will feel comfortable to understand the concept of instruction level parallelism, where our focus will be the floating point data. So today I will end at this stage, and I say you Allah Hafiz.